Okay, in this video, I am going to give out the solution to handout 5. So let's start with example 1. So in this example, we are asked to calculate the electric charge and the electric current. So the question is, electric charges Q coulombs flow through a substance. At time t seconds, the charge is given by Qt is 3t squared plus t plus 3. A. Calculate the electric charge at t equal to 1.3. So we just substitute t equal to 1.3 into these equations. So we are going to get 3 times 1.3 squared plus 1.3 plus 3. And this is 9.37 coulombs. In part B, we are asked to calculate the electric current. So we know that the current I is dq by dt. So we differentiate this function. So we get 6t plus 1. And at t equal to 1.3, the current I is 6 times 1.3 plus 1 is 8.8 amperes. Example number two, a charged belt. So we've got a belt and we've got charged on this belt. Assume that these charges are positive. 50 centimeter wide. So this side here is 50 centimeter. Travels at the speed of 30 meter per second. So the speed here is 30 meter per second. The bell carries charge into the sphere at a rate of, so I mean dq by dt, the rate of change of charge, which is 76 microampere. So it means microcoulomb per 1 second. A. Compute the surface charge density. So let's think about this problem. Suppose that in 1 second, this bell has moved through the distance of 30 meter. So we know that the area A is 0.5 times 0.3 meter square. And the charge on this belt in 1 second is 76 microcoulomb. So we have 76 microcoulomb. So in part A, compute the surface charge density. So sigma is Q over A. So we have 76 microcoulombs divided by 0.5 times 0.3, and the answer is 5.1 times 10 to the power of minus 4 coulomb per cubic meter, per square meter. So this is the answer of part A. In part B, what is the number density per unit area of electrons on the belt? So we know that we have the charge in 1 square meter. So what else do we know? We know that 1 electron has charge of 1.6 times 10 to minus 19 coulomb. So now if we want to get the number, we just divide this number 5.1 times 10 to minus 4 by 1.6 times 10 to minus 19. So we get the number of electron per square meter, and this is 3.2 times 10 to the power of 15 electrons per square meter. Example number 3. Example number 3. Lightning strikes the ground and spread over a hemisphere under the ground with the current I. So you see that this is the ground. The lightning strike at this point. We assume that the ground is homogeneous, so the electric current is spread out in all directions. So we get hemisphere. I is 5.2 times 10 to the power of 4 amperes. We want to get the current density J. So J is I over A, and the area A here is half of the sphere. So we have A equal to 2 pi r squared. So we have 5.2 times 10 to the power of 4 divided by 2 pi times the radius r, which is 1.5 square. So the answer is 3.7 times 10 to the power of 3 ampere per square meter. Next, we are looking at example number 4. Estimate the average drift velocity Vd of the electrons in a copper wire of radius r equal to 2 mm carrying current I equal to 25 amperes. Assume that each copper atom contributes 1 electron to the drift current, that the relative atomic mass of copper is 63.5 and the density is 8.9 times 10 to the power of 3. So we know that I equal to VANE. So if we want V, it is equal to I over ANE. We already know I, A, and E. What we don't know is this N, which is the number density, the number of electron per cubic meter. So let's think about it. We know that in 1 cubic meter, we have copper of weight 8.9 times 10 to the power of 3 kilogram. Now we change this kilogram to number of copper atoms. So we have 8.9 times 10 to the power of 3 divided by. So we know that one atom of copper, one copper atom is weight about 63.5 times 1.67 times 10 to the power of minus 27. So we divide this by 63.5 times 1.67 times 10 to the power of minus 27. Now we've got number of copper atom, but one copper atom give out 1 electron. So this is also the number of electron in 1 cubic meter as well. So N is actually 8.9 times 10 to the power of 3 divided by 63.5 times 1.67 times 10 to the power of minus 27. And this gives us 8.39 times 10 to the power of 29. So we have V equal to I over ANE, and this equal to 25 over A, radius of 2 millimeters. So we have pi times r squared times N, which we've got 8.39 times 10 to the power of 29 times 1.6 times 10 to the power of minus 19. So we've got 25 divided by pi divided by this divided by square. So we've got it about 1.5 times 10 to the power of minus 4 meter per second. This number is very slow. It's very slow, but it's correct. Now let's look at question example number 5. Let's look at example number 5. So we have calculated the resistance of copper rod of length. So we've got copper rod. The length L is 30 centimeter. The radius R is 0.5 centimeter. The resistivity rho is 1.7 times 10 to the power of minus 8 ohm meter. So we know that R equal to rho L over A. So we plug in the number, change centimeter to meter, is pi R square. Six 6.5 times 10 to the power of minus 5 ohm. So this is the resistance of the copper wire. Next is example number 6. A hollow conducting cylinder of length L, the inner radius is RA and RB respectively. The resistivity is rho. We say that the current, so if we look it from top view, it will be like this. We've got inner and outer. The current flow out radially in this direction. The current flow in these directions. So what happened when we look at it, when we look at this problem? We say that the current flow through a thin sheet of cylindrical shell like this. So this distance is R, the thickness here is dr. So this dr is actually L in this equation, rho L over A. So we have dr equal to rho times dl, which is dr, and the area A is the area of the surface area of the cylinder. So it's 2 pi RL, 2 pi RL. To get the total resistance, we integrate both sides. So we've got R equal to rho over 2 pi L. We integrate dr over R from the inner to the outer. So we've got log RB over RA. And we've got the answer. Next is example number 7. So we got a nichrome wire consists of a nickel chromium ion alloy. Is commonly used in heating element. The conductivity sigma is 2 times 10 to the power of 6. The wire with cross-section area A 2.3 what is it? 2.3 millimeter square. And then the current I is given by 5.5 ampere. The potential difference V is 1.4, and then we are asked to calculate the length of this wire. So how should we do this? We know that Ohm's law say V equal to I times R. And we know that R equal to rho L over A, but rho is the inverse of conductivity sigma. So we have this equation. Plug this R into this equation. You've got V equal to I times L over sigma A. So L is V sigma A over I. So we have V equal to, or not V, sorry, we've got L equal to V 1.4 times sigma 2 times 10 to the power of 6 times 2.3 times 10 to the power of minus 6 divided by the current 5.5. Then type in this calculator. (1.2). So this L is 1.2 meter. 1.2 meter. Next example is example number 8. 850 watt radiant heater is operated at 115 volt. What is current? Using P equal to I times V. So we know that P is 850, I times 115. So the current I is 7.4 ampere. B, what is the resistance of the heating coil? We are going to use V equal to I times R. V is 115, I is 7.4. So R is 15.6 ohm. C, how much thermal energy is produced in 5 hours? So we know that P is E over T. So E, energy, is P times T. Is it 850 times 5 hours? 1 hour is 60 minutes, and 60 minutes is 60 seconds. So we have 850 times 5 times 60 times 60. So we've got 1.53 times 10 to the power of 7 joules. Next and the last question, example 9. A copper wire having cross-section area 2.4 times 10 to the power of minus 6. A is 2.4 times 10 to the power of minus 6 meters square, and length L is 4 meter. Current I is 2 amperes. Find the magnitude of electric field along the wire. So this is L. We know LIA. Copper wire, we know resistivity. The resistivity of this copper wire is rho is 1.7 times 10 to the power of minus 8. So we have to use this information from example number 5. So first calculate R. R is rho L over A. So we've got this times 4 over area A, 2.4 times 10 to the power of minus 6. Which is about 0.03 ohm. And when we know R, we know the potential difference V across these two. So V equal to I times R. So I'm going to multiply this number by 2 amperes. And the potential difference is 0.057 volts. The electric field E is V over D, so V over L. So we have 0.057 divided by L, which is 4 meter. And this is 0.014 volt per meter. So this is the answer of part A. How much electrical energy is transferred in 30 minutes? So we know that P is E over T, and this equal to I square R. So E is I square R times T. So we have times V, and then we times it with I again, and then we multiply it with T, 2 minutes, 30 minutes, 30 times 60, so we get 204 joules. So this is the answer. Hope this video helped with your revision.